I've realized that I made a mistake in what I thought was the solution to this second solitaire problem. My mistake was in thinking, I realized that I wanted phi to be bigger than 1. Then I thought that the most that you could reduce the invariant by was 2 phi, but actually the further out you are, the more you reduce the invariant by in this particular, when phi is bigger than 1. It'd be sort of 2 times some power of phi, and so therefore what I did was not correct. I just want to see whether I can salvage a correct proof out of this, and I think the thought I had, and if it doesn't work quickly then I'll just stop, but the thought I had was that phi satisfies phi squared equals phi plus 1, and so 1 over phi satisfies that 1 over phi squared equals plus 1 over phi equals 1. So if I call that psi, psi squared plus psi equals 1. So if my invariant now is going to be the sum over all chips of psi to the x plus y, this is again back to the 3 by 3 case. What happens when I do a move that goes in an outward direction? I replace, say I started from 0, I'd replace 1 plus psi by psi squared. And 1 plus psi so that is changing things. But if I go inwards, then I'm replacing, say I'm replacing psi squared plus psi by 1. So if I go inwards, things remain invariant, but if I go outwards, they don't. What happens if I go outwards? So 1 plus psi minus psi squared equals 1 plus psi minus, psi squared is 1 minus psi, equals 2 psi. So if I start with 1 plus psi and end up with psi squared, then I am subtracting 2 psi. So inwards invariant, outwards subtract 2 psi. And number of moves, 8. Starting value, so these calculations are going to be rather similar to what I had before. 1 plus, and then there are 4 that are at distance 1, so 4 psi, and 4 that are at distance 2, 4 psi squared. But I've got to be a little bit more careful here. So it's psi squared plus psi equals 1. So this equals 5. So most we can subtract. Is 16 psi. And so far that's not great, because 16 psi is bigger than 5. and so the ending value is 1. So we would need 16 psi less than 4, which is nowhere near true. But on the other hand, it is also not true that we're going to be subtracting 2 psi every single time. Because that would, so here for example, I subtract 2 psi, but up here, the only way of subtracting 2 psi is if I have a something on 0, something on 0, 0, something on a neighbouring point, and then I get to the point after that. So with a little bit more care, it should be possible to argue that what we can subtract is a lot less than 16 psi. And moves coming so I can subtract 2 psi once, but then to do it again I'd have to get something onto 0. To get something onto 0 I'll have to that's actually going to be quite difficult. In fact, it's hard to see how to do it at all. And of course it's not absolutely obvious this is going to be the invariant I really want. Let's just have a little think about what happens if I do this move. So I've subtracted 2 psi there from the invariant, but here I'm only going to be able to subtract, so the next move, the most I can possibly subtract, and I think this will be what I subtract, whatever I do is going to be 2 psi squared. Let's try that one. If I do this, what will I subtract? Then that had 1 psi squared, so I'll just lose the psi squared, but this, the value of this will be the same as the value here. So I could subtract I can sort of see myself managing to subtract another 2 psi squared or 2, so that could be a 2 psi squared. That one could be a 2 psi squared. Not a clever thing to do exactly, but wait, so if I did this, I'll just so I did 1 move, 2 moves, and a third move, subtracted 1. Wait a minute, subtracted just a psi squared, I mean. Just check, I've done 9, I'm down to 6, I've done 3 moves, yes. Here I'm going to subtract, where was the origin? The origin was there. So it's psi plus psi squared goes to psi cubed. If that was subtracting 2 psi, this is going to be subtracting 2 psi squared. And then here I can subtract, that one subtracts whatever this is, which is psi. And so how much have I subtracted so far? 5 psi squared plus 3 psi, which is getting dangerously close to, which equals, so psi squared plus psi is 1, so 5 squared plus 5 psi is 5, so that's 5 minus 2 psi. So it's getting sort of a little bit dangerously close to to 4. What's the best I can subtract? So if it's coming inwards, makes me subtract. No, it makes me subtract less. It's the outward moves that do the subtracting. So if I went outwards here and outwards here, that one subtracted 2 psi, so it subtracts 2 psi squared, so I can subtract another 4 psi squared. So what do I get for 9 psi squared plus 3 psi? That equals, so 9 psi squared plus 9 psi would be 9. So that's 9 minus 6 psi versus 5. So what I would very much like is for 9 minus 6 psi to be less than 5. So I want 4 to be less than 6 psi. And 6 psi is at least as big as 6 times 1.6, which is 9. Oh, that's easy. Sorry, that's obviously true. But did I? But I didn't. I wanted it to be 4. So that means I needed 5 to be less than 6 psi, but that's still obviously true. So that wasn't really a proof. It was just a kind of argument that I would have to do enough enough inward moves, or enough moves that were not, unfortunately, that were not close to the origin. I wouldn't be able to subtract enough stuff. Let me just proceed to the general case quickly. Or the 5 case, perhaps. So we want to argue that we subtract as much as possible, but what we could say is that when I move or take a given piece, let's go by which piece I take. So for example here, there should be an argument that says when I start, I'm actually only going to be able to, the most I'm going to be able to subtract because I'm near the boundary, so I can't do anything in the middle yet. I'm not going to be able to subtract anything like as much as 2 psi. In fact, the amount that I'll be able to subtract is going to be get smaller and smaller as I get further and further out. And at each step, I somehow want to argue that when this piece disappears, the most that's going to happen, so all but one piece will disappear from where it is, either by moving or by being taken. So we could say, what's the most that we're going to be able to subtract when this piece disappears, except it might disappear more than once. So is that a problem? Maybe we could look at the path that a piece takes, but that's not really quite enough. That's what I want to try to argue. So how much does the invariant have to come down by? Let's just do that calculation once more. It's 1 plus 4 psi plus 8 psi squared plus 8 psi cubed plus 4 psi to the fourth. But now things are slightly different, because instead of having phi squared equals 5 plus 1, we have psi squared plus psi equals 1. So this 8 psi squared plus 8 psi cubed is 8 psi times psi plus psi squared, so it's 8 psi. But that actually doesn't help me simplify. Let's simplify in the other direction. So a 4 psi to the fourth plus a 4 psi cubed is a 4 psi squared. So we get 1 plus 4 psi. So I get 4 psi squared, and I have to subtract 4 psi cubed and 4 psi to the fourth. Now the 4 psi squared plus 4 psi cubed equals 4 psi. So that's 1 plus 8 psi. That's how big the invariant is. And I want to argue that I can't. That's how big it is to start with. So I need to subtract a total of 8 psi. And I want to argue that that's going to be very difficult to do. So if I were to just move all those ones, just to be as greedy as possible, then that would get me, so if that gets me 2 psi, that means that gets me 2 psi squared. Then I have 2 psi cubed plus 2 psi to the fourth. That's dealt with those ones. So I can then repeat that 4 times. Get 8 psi squared plus 8 psi cubed plus 8 psi. So I can certainly subtract that much from the invariant. So how does that compare with 8 psi? 8 psi equals 8 psi squared plus 8 psi cubed. So unfortunately this is bigger than 8 psi. So it seems as though this additional idea doesn't work, and at that point I will stop and declare that I have not managed to solve this IMO problem after all, and I'm not sure I'm going to try and solve it on video. Actually, I might think about it privately at some point and come back if I manage to solve it. So don't feel quite so good as I did before.